Good morning, students. Myself, Dr. Monika Khetarpal. I am Associate Professor of Physics in Government Dungar College, Bikaner. I welcome you all in an important lecture of MSc Previous Physics. I am dealing with the first paper, that is Classical Mechanics. Students, I am going to today discuss some important questions which can which will be beneficial for you for the purpose of NET or JRF exams. For this purpose, you must know the basic concepts of Lagrangian and Hamiltonian. So, I am starting with the first question, that is, I have been given that potential of a diatomic molecule as a function of distance r between the atoms can be expressed as Vr equal to minus a upon r raised to power 6 plus b upon r raised to power 12. Then I have to find the value of potential at equilibrium separation between the atoms. Here a and b are constants. As in the question, we have mentioned that we have to find the value of potential at equilibrium. That means we are given a condition that del V by del R will be 0. Because at equilibrium VR will have an extremum value, so derivative will be 0. Obtaining the derivative from this expression, I get, on solving, the value of R as 2b upon a whole raised to the power 1 by 6. I have to find the value of v. So in the value of v, instead of R, I have to put 2b upon a raised to the power 1 by 6. So substituting the value, I get the value of potential energy as minus a square upon 4b. So this was a basic concept of equilibrium position. That means the position at which V must have an extremum value, so its derivative must be equal to 0. The next question is of a particle of mass m which move inside a bowl, and the surface of the bowl is given by z equal to half a x square plus y square, a being the constant. I have to find the value for Lagrangian of the particle. As we are given a particle inside a bowl, it will be cylindrical in shape. So we have to use a cylindrical coordinate system. And we know that in the cylindrical coordinate system, it is three-dimensional view. So we have Lagrangian to be expressed as half m x dot square plus y dot square plus z dot square. The value of z is given in our problem. As the coordinates are cylindrical, we can express r, x and y as x to be r cos phi, y as r sin phi, and z, which we have given half a x square plus y square. X square plus y square can be expressed from these equations as r square. So we have obtained the value of x, y and z. Now we can find the value of their derivatives, that means x dot, y dot and z dot. And finding the values, we can easily obtain the value of Lagrangian of the system. x dot will be, as there are two terms, two functional dependence r and phi, r dot cos phi minus r sin phi, phi dot. Similarly, from here we can find y dot, and from this expression we can find z dot as ar r dot. So, obtaining these values, I can substitute them to obtain the value of Lagrangian of the system. The next problem is Lagrangian is given. We have to find Hamiltonian. So, for this purpose, we must know the relation between L and H. Since this problem is simply given in only one dimension, so we have to solve it only in one dimension, that is x direction. The relation between L and H is H equal to summation Pj Qj dot minus L, as only one coordinate is there and that is x. So H will be Px x dot minus L. So in order to find the value of Hamiltonian, initially I have to find the value of generalized momenta. Generalized momenta Pj has formula del L by del Qj dot, and for in this problem Px will be equal to del L by del x dot, as generalized coordinate Qj equal to x. So differentiating L with respect to x dot, I get it as x dot upon x. From here I can write x dot to be equal to Px into x. Hence my Hamiltonian, which is Px x dot minus L, on substituting the value of x dot and L, it comes out to be H equal to Px square multiplied by x divided by 2 plus V. So we must know the relation between Lagrangian and Hamiltonian of the system in order to solve the problems. In the next problem, we are given that there are three particles. These are the three particles and the masses of all the three particles are equal, and they are connected by springs. The springs are massless and identical, and the spring constant is K. We have to determine the potential energy of the system, and we are given that x1, x2 and x3, these are the horizontal displacement of masses from their equilibrium position. Now, if there were only these two masses and the displacement were x1 and x2, then simply the potential energy will be half k x2 minus x1 square. But as we have one additional spring more and there is also an horizontal displacement in this spring also, so by taking into account its potential energy, which is half k x3 minus x2 whole square, we have our effective potential energy for two spring masses which are connected horizontally. In the next problem, we are given a Lagrangian of a particle of mass m in one dimension, given by half m x dot square minus bx. Here b is a constant. The coordinate of the particle at time t is our problem to be determined. So in order to find the coordinate, that means x, we are solving the Lagrangian equation of motion. This is our Lagrangian equation of motion. The general Lagrangian equation is d by dt del L by del Qj minus del L by del Qj. Qj means generalized coordinate, which for our problem is x coordinate. So we have expressed our Lagrangian equation as d by dt del L by del x dot minus del L by del x equal to 0. On solving the differential of L with respect to x dot, I get as mx dot, and differential of L with respect to x, this will give me b. So mx double dot plus b equal to 0. So I have x double dot to be equal to minus b by m. I have to find the position, that means x. For this purpose, I am integrating the double differential equation. So I get dx by dt to be minus b by m multiplied by t plus a constant of integration c1. Further integration gives me the value of x, which is the unknown parameter which we have to find. X comes out to be minus b by m t square by 2 plus c1t plus another constant of integration, which is denoted here by c2. So this is the value of displacement at time t. So these are the some basic questions related to the Hamiltonian and Lagrangian approach. Thank you students for watching.